The square root of 5 is the positive real number that, when multiplied by itself, gives the prime number 5. It is more precisely called the principal square root of 5, to distinguish it from the negative number with the same property. This number appears in the fractional expression for the golden ratio. It can be denoted in surd form as it is an irrational algebraic number. The first 60 significant digits of its decimal expansion are 2.23606797499696408954257242772425702427089, which can be rounded down to 2.236 to within 99.99% accuracy. As of December 2013, its numerical value in decimal has been computed to at least 10 billion digits. Proofs of irrationality. This irrationality proof for the square root of 5 uses Fermat's method of infinite descent. Suppose that square root 5 is rational, and express it in lowest possible terms as for natural numbers m and n. Then square root 5 can be expressed in lower terms as, which is a contradiction. This irrationality proof is a proof by contradiction. Suppose that where is in reduced form. Thus an if b was even, and a would be even, making the fraction not in reduced form. Thus b is odd, and by following a similar process a is odd. Now, let and where m and n are integers. Substituting into we get, which simplifies to making by subtracting 1 from both sides, we get, which reduces to, aka the expression is even for any integer. So what this is saying is, 5 times even plus 1 equals even, or odd equals even. There is no integer that's both even and odd, thus we've reached a contradiction in as irrational. Continued fraction. It can be expressed as the continued fraction 2, 4, 4, 4, 4, 4. The sequence of best rational approximations is convergence of the continued fraction are colored blue. Their numerators are 2, 9, 38, 161, and the denominators are 1, 4, 17, 72. The other terms are semi-convergence. Babylonian method. When is computed with the Babylonian method, starting with r0 equals 2 and using rn plus 1 equals 2. The nth approximant Rn is equal to the 2 nth convergent of the convergent sequence. Relation to the golden ratio and Fibonacci numbers. This golden ratio is the arithmetic mean of 1 and the square root of 5. The algebraic relationship between the square root of 5, the golden ratio, and the conjugate of the golden ratio, the square root of 5, then naturally figures in the closed form expression for the Fibonacci numbers. A formula which is usually written in terms of the golden ratio, the quotient of square root 5 and its reciprocal, provide an interesting pattern of continued fractions and are related to the ratios between the Fibonacci numbers and the Lucas numbers. The series of convergence to these values feature the series of Fibonacci numbers and the series of Lucas numbers as numerators and denominators, and vice versa, respectively. Geometry. Geometrically, the square root of 5 corresponds to the diagonal of a rectangle whose sides are of length 1 and 2, as is evident from the Pythagorean theorem. Such a rectangle can be obtained by halving a square, or by placing two equal squares side by side, together with the algebraic relationship between square root 5 and phi. This forms the basis for the geometrical construction of a golden rectangle from a square, and for the construction of a regular pentagon, given its side, forming a dihedral right angle with the two equal squares that halve a 1 to 2 rectangle. It can be seen that square root 5 corresponds also to the ratio between the length of a cube edge and the shortest distance from one of its vertices to the opposite one, when traversing the cube's surface. The number square root 5 can be algebraically and geometrically related to the square root of 2 and the square root of 3, as it is the length of the hypotenuse of a right triangle with catheti measuring square root 2 and square root 3. Right triangles of such proportions can be found inside a cube. The sides of any triangle defined by the center point of a cube, one of its vertices, and the middle point of a side located on one the faces containing that vertex and opposite to it, are in the ratio square root 2, square root 3, square root 5. This follows from the geometrical relationships between a cube and the quantities square root 2, square root 3 and square root 5. A rectangle with side proportions 1, square root 5 is called a root 5 rectangle and is part of the series of root rectangles, a subset of dynamic rectangles, which are based on square root 1, square root 2, square root 3, square root 4, square root 5, and successively constructed using the diagonal of the previous root rectangle, starting from a square. A root 5 rectangle is particularly notable in that it can be split into a square and two equal golden rectangles, or into two golden rectangles of different sizes. It can also be decomposed as the union of two equal golden rectangles whose intersection forms a square. All this can be seen as the geometric interpretation of the algebraic relationships between square root 5, phi and phi mentioned above. The root 5 rectangle can be constructed from a 1 to 2 rectangle, or directly from a square in a manner similar to the one for the golden rectangle shown in the illustration, but extending the arc of length square root 5 halves to both sides. Trigonometry. Like square root 2 and square root 3, the square root of 5 appears extensively in the formulae for exact trigonometric constants, including in the sines and cosines of every angle whose measure in degrees is divisible by 3 but not by 15. The simplest of these are as such the computation of its value is important for generating trigonometric tables. Since square root 5 is geometrically linked to half-square rectangles and to pentagons, it also appears frequently in formulae for the geometric properties of figures derived from them, such as in the formula for the volume of a dodecahedron. Diophantine approximations. Hurwitz's theorem in Diophantine approximations states that every irrational number x can be approximated by infinitely many rational numbers m n in lowest terms in such a way that square root 5 is best possible, in the sense that for any larger constant than square root 5, there are some irrational numbers x for which only finitely many such approximations exist. Closely related to this is the theorem that of any three consecutive convergence bar chi, pi plus 1, chi plus 1, pi plus 2, chi plus 2, of a number alpha, at least one of the three inequalities holds, and the square root 5 in the denominator is the best bound possible since the convergence of the golden ratio make the difference on the left-hand side arbitrarily close to the value on the right-hand side. In particular, one cannot obtain a tighter bound by considering sequences of 4 or more consecutive convergence. Algebra. The ring contains numbers of the form, where a and b are integers and is the imaginary number. This ring is a frequently cited example of an integral domain that is not a unique factorization domain. The number 6 has two inequivalent factorizations within this ring. The field, like any other quadratic field, is an abelian extension of the rational numbers. The Kronecker-Weber theorem therefore guarantees that the square root of 5 can be written as a rational linear combination of roots of unity, identities of Ramanujan. The square root of 5 appears in various identities of Ramanujan involving continued fractions. For example, this case of the Rogers-Ramanujan continued fraction.